So welcome to this presentation. Now we are going to discuss the question and the answers regarding the selective precipitation. Let's start on question number 21 because last time we have ended number 20. Question number 21 is saying silver nitrate was added to the solution containing a mixture of 0.001 molar of potassium iodide. So here you can determine the concentration of iodide, and 0.1 molar potassium chloride. So that means here we can also get the concentration of chloride. Which compound will precipitate fast between the silver chloride and the silver iodine? That means when we add silver nitrate, silver will react with the iodine to give the silver iodine, and then silver again will react with chloride to give the silver chloride. They are also asking determine the concentration of the silver at which the silver iodine and the silver chloride will start forming the precipitate. The KSP of the silver chloride was given, and the KSP of silver iodine was also given. You can see that this one is the one which has the less KSP as compared to this one. So let's go to answer. We need to compare the KSP of two compounds. You compare this one and this one. We can see the silver iodine, which is this one, is the one with less KSP. You can see it is having 10 to the power negative 16 as compared to 10 to the power negative 10. So that means it is the one which is less soluble as compared to silver chloride, and it is the one which will precipitate before silver chloride. So the silver iodine is the one which will precipitate before silver chloride, just because it is having less KSP, it is less soluble as compared to silver chloride. So it is the one which will precipitate before the silver chloride. Then they are asking determine the concentration of the silver at which the silver iodine and the silver chloride will start forming the precipitate. We just replace the values. So here we have the KSP expression. Now they are asking the concentration of the silver. Then the chloride concentration, you have it in the question. Then we replace the value, and then we get the concentration of silver at which the silver chloride will start to precipitate. So that means silver chloride will start to precipitate when the silver concentration is 1.8 times 10 to the power negative 9 molar. So we just replace the value of the KSP and the value of the chloride concentration, and then we determine the concentration for the silver. So we proceed again for the silver iodine. It's also the same. We write the KSP expression. Then we have the KSP, it was given in the question. Then we have also the concentration for the iodine. Then we determine the concentration of the silver. So we found that the silver iodide will start to precipitate when the silver concentration is 1.5 times 10 to the power negative 13 molar. So if you compare the two values, this one and this one, you can see that this one is less as compared to this one. So which means that the silver iodine will start to precipitate at low concentration as compared to silver chloride. So even if you compare the concentration of silver at which the two compound will start to precipitate, you can see that the silver iodide is the one which will form precipitate on the first time as compared to this silver chloride, because this one requires less concentration of the silver to precipitate as compared to silver chloride. So let's go to question number 22. Question number 22 is saying solution is composed of the mixture of 0.1 molar NiCa and 0.1 molar kappa 2 plus. Students want to separate the two ions using selective precipitation by adding sodium carbonate. So that means the carbonate react with the NiCa to give NiCa carbonate, and the carbonate react with copper to give copper carbonate. They're asking, assuming no volume change after the addition of sodium carbonate, how much of the first ion in percentage remains, and how much precipitates at the point where the second ion begins to precipitate. Here, we need to know which ion will precipitate first and which one will precipitate on the second time, so that we can determine how much will be remaining into the solution, how much of the first ion will be remaining into the solution, and how much will be precipitating. So let's first see which one is going to be precipitating first and which one will be precipitating on the second time. So we are going to see it by comparing their KSP. So if we compare the KSP, we can see that the copper carbonate is less soluble. You can see copper carbonate is having 10 power negative 10, so it's the one which is less as compared to 10 power negative 7. So the copper carbonate is less soluble as compared to nickel carbonate. So that means the copper carbonate will precipitate fast and the nickel carbonate will precipitate on the second time. So this nickel carbonate will precipitate on the second time, then the copper carbonate is one which will precipitate on the first time. So now they are asking when this nickel carbonate, which will precipitate on the second time. So when this nickel carbonate start to precipitate, they are asking what will be the concentration of the copper remaining into the solution. So that's what they are asking. So what we do, we just add the carbonate to precipitate the second ion, to precipitate the nickel, because nickel is the one which will precipitate the first. Then we find the concentration of the carbonate to precipitate nickel, and then after finding the concentration to precipitate the second ion, then we can determine how much of the first ion will be remaining to the solution at that concentration of the carbonate. What will happen is that the copper carbonate will start to precipitate first, so the new equilibrium will be established. Then the copper carbonate will precipitate, decreasing the concentration of copper in the solution until the equilibrium is established. That means we will be adding carbonate, and then the carbonate will react with the first ion which will be precipitating first, which is copper. Then a new equilibrium is established. Then again we continue to add the carbonate. Then the carbonate reacts with the second ion, which is nickel. Also, then after reacting with nickel, a new equilibrium is going to be established. So the nickel carbonate will start then precipitating after copper carbonate, and then a new equilibrium will be established. Then from that equilibrium, we can determine how much of copper will be remaining into the solution when the second ion, which is nickel, start to precipitate. So if we can find the carbonate required to precipitate the nickel, which is the second ion which is going to precipitate, then we can use the required carbonate to find out the concentration of copper that will remain in the solution after nickel start to precipitate. That means we are determining the concentration of the carbonate to precipitate the second ion. Then we use that concentration to calculate how much of the first ion will be remained into the solution. So now, what is the concentration of the carbonate required to precipitate the second ion? So we use the expression of the KSP. We have determined that the nickel is the one which we precipitate on the second time. So we determine how much carbonate is required to precipitate the nickel, the one which we precipitate on the second time. So we calculate, we have the carbonate concentration which is need to be calculated. The nickel concentration, it was given, the KSP was also given. So then we find the carbonate which is needed so that the nickel start to precipitate. So we obtain this concentration. That means that this concentration of the carbonate, so the second ion, which is the nickel, will start to precipitate. Then we can determine at this concentration of carbonate how much of the copper will be remaining into the solution. So we use the expression, then we replace this concentration of the carbonate, then we determine how much of the copper will be remaining to the solution. The KSP of copper carbonate was given. So we obtain that this is the concentration of the copper that will be remaining to the solution. So we can calculate then the percentage of this concentration, the percentage of the copper that will be remaining to the solution by taking this one, dividing with the initial times 100. Then we know how much the percentage of copper will be remaining in the solution. We obtain 0.18%. Now to obtain how much precipitate, we take 100 minus the percentage which is remaining to the solution. Then we see that the percentage of the copper left in the solution will be 0.18%, and the percentage of the copper precipitated will be equal to 99.82%. So when you have such kind of questions, you determine how much required to precipitate the second ion, then use that concentration to determine the amount of the first ion that will be remaining into the solution. Because when the second ion is going to precipitate, a new equilibrium will be established. then we calculate how much of the first ion will be remaining the solution after the equilibrium is established. Let's see question number 23. Question number 23 is saying a solution is 0.02 molar in both cadmium and nickel, so they have the same concentration, which will precipitate first between cadmium S and also nickel S. So here we have the cadmium that will react with the sulfur, so that we have cadmium S and then nickel S. So they are asking which one will precipitate first. So we are going to compare the KSP to find which one will precipitate first. They're asking just before nickel S beginning to precipitate. So just before nickel S beginning, what concentration of cadmium will be left in the solution. Let's see which one will be forming the precipitate on the first time. So we have nickel S, which is 10 power negative 21, and here we have 10 power negative 29. So obviously this is the one which is less soluble. So that means the compound which is less soluble. So that means the one which will precipitate first. So comparing the two compounds, you can see the cadmium S, which is less soluble, is the one with less solubility, less KSP. Then in that case, we will precipitate first. So cadmium S will precipitate first, and then nickel S will precipitate after the cadmium S. So this one, then we have after knowing that the nickel S will be precipitating after, then we determine how much of the sulfur is required to precipitate the second ion, which is nickel. Then we use that concentration to find how much cadmium will be remaining into the solution when this nickel S start to precipitate. So the equilibrium will be established after nickel S will also precipitate, and a new equilibrium will be established. That means the first precipitate will be formed, equilibrium established. The second precipitate also formed, a new equilibrium again established. Then at that equilibrium, so we calculate how much to precipitate the second ion. Then we use that amount to calculate how much will be remaining to the solution. So here we find the concentration of the sulfur ion when nickel just beginning to precipitate. That means when the second ion beginning to precipitate. Then use this concentration of the sulfur to find how much cadmium will be remaining to the solution. So here then we have the KSP for the nickel S. So we determine how much of the sulfur is required to precipitate the second ion, which is nickel. So we calculate it, and then we obtain the concentration which is equal to 1.5 times 10 power negative 19 molar. So this is the amount of the sulfur which is required to precipitate the second ion, which is nickel. Then we use this amount to calculate how much of the cadmium will be remaining the solution using the expression. Here then we replace the KSP, we replace the value of the S, the sulfur, then we determine the cadmium. So that means 2.6 times 10 power negative 10 molar of cadmium will be remain the solution after the second ion precipitate, just after nickel form a precipitate. Let's go to question 24. Question 24 is saying the KSP of barium sulfate is this one, and the barium selenate is this one. So you can see here we have the sulfate concentration and you have the selenate concentration. Then they are asking a 1 molar solution of barium chloride is added slowly to a solution that is 10 power negative 4 molar sodium sulfate and 10 power negative 4 molar sodium selenate. So if we have the concentration of here we have the KSP of the two, KSP of barium sulfate and the KSP of the barium selenate. We have also their concentration. Here we can find the concentration of the sulfate, and then we can find the concentration of the selenate. This one was the KSP. We have this KSP. Here we have the KSP. So then if we add 1 molar solution of barium chloride, that means this barium will react with the sulfate, and barium here will react with the selenate. Then they're asking what is the percentage of the first ion that has precipitated at the point that the second anion is just beginning to precipitate. Here also we need to check between the selenite ion and the sulfate ion, which one is going to precipitate fast by comparing on the Ksp, their Ksp. So we have two anions, so sulfate and selenite, and they all need barium to precipitate. So barium selenite will precipitate on the first time because it has the less Ksp than barium sulfate. So you can see that here we have 10 power negative 11. So that means the selenite is the one which usually precipitate on the first time because it is less soluble compared to 10 power negative 10 of sulfate. So then, as long as we know the one which will precipitate on the second time, then we determine how much required to precipitate the ion which will precipitate on the second time. Then we use that concentration to calculate how much will be remaining to the solution and how much precipitated, of course. Here then we calculate the barium required to precipitate the sulfate, because the sulfate is the one which will precipitate on the second time. Then after finding that barium required to precipitate the sulfate, we use that barium to calculate how much of the selenite will be remaining to the solution. So here we have the Ksp, we calculate the barium required to precipitate the sulfate. So we get 1.1 times 10 power negative 6 molar. Then we use that barium concentration to find out the selenite concentration that will be left into the solution. So we use the expression, we have the barium, then you calculate how much selenite will be remaining to the solution. So we find that the concentration that will be left into the solution, it will be equal to 2.55 times 10 power negative 5 molar. So then after getting the concentration which will be left into the solution, you can determine how much will be precipitated by taking the initial minus the one left in the solution. Then we get the one which form the precipitate. So the percentage precipitated, then we take the concentration which make precipitate dividing with the initial concentration times 100, then we get 74.55%, so as the percentage of the selenite which is precipitated. So that was the package of today. Then next time we see the question and the answer regarding solubility and the common ion effect.